Good morning. Today I will start ESP, some calculations. Last class I have seen you have seen that there is electrical system and we have done some calculation also. Now today we will try to go for calculation with pumping systems. We'll try to understand more details about pumps and how intake is happening, how fluid is flowing, how heat generation is happening. Before we go for calculation, we have to know some basics of the pumps. Although sometime it will be a recap of the previous lectures. Let's see the pump first. Okay, you have seen this one. I have shown already you. So this is the flow passage. Okay, this is impeller eye. So impeller eye I will draw here. Impeller eye is here, and my impeller, if I draw like this, it is having a curved blade, right? So blade will be 5, 6, 7, so within that range, not like 100 to 100. Okay, now this is, there will be one shaft hole. Okay, so fluid is entering through this gap. Actually there will be some gap. Okay, so this is called impeller eye, and these are blades. Okay, so impellers are having blades, and rotation direction, like this will be the rotation direction of the impeller. Okay, this will be rotation direction. So impeller is here. So if you see the curve, okay, so it will be rotating like this. It will be rotating like this. Okay, not opposite. It is rotating like this. When it is rotating, this blade will get one suction surface, one pressure surface. What is suction surface? What is pressure? So let's assume this is my blade. Okay, and blade is rotating in this direction. Okay, okay, or vane, someone say. Okay, these are impeller blades. The blade is rotating. Because of rotating, fluid will be passing through this channel. So this channel is here. Okay, fluid flow channel. Flow. Okay, so fluid will be moving like this, and when it is moving, this area, this blade, this surface will be pressure surface. Okay, this surface will be suction surface. So this is pressure surface. Pressure surface, and this area will be suction surface. Okay, suction. Sometimes people will write suction side, sometimes they will be writing pressure side. I say suction surface and pressure surface. So when it is rotating, this area will be getting higher pressure from fluid. Okay, so that's it, pressure surface. But opposite of this area of pressure, okay, blade vertically, if you see this area pressure, so opposite of this one, this area suction. Okay, when it is rotating, this area will get more pressure, this area will get less pressure. So this pressure suction of this one, so one blade pressure surface, another blade suction surface, in between there is channel. Okay, that channel will be flowing from impeller eye to impeller exit. So this is eye area and YE. Okay, and this is impeller exit area. This is exit area. Okay, this area exit. Okay, if I have 5, 6, 7, 8, 9 blades, so normally blade will be like 5, 6, 7. So within that range. Here I have 1, 2, 3, 4, 5 blades. I have 5 blades. 1, 2, 3, 4, 5. Okay, I have 5 blades, helically curved. Okay, this is helical blade, and this is radial flow impeller. Whatever I am showing you, it is radial flow because fluid is entering axially, it is turning vertically. I mean perpendicular to axis. There is one shaft, one keyhole is here. So shaft will be like this. Okay, and fluid will be going axially and it is going vertically. Okay, perpendicular to shaft. So that's why it is radial flow. There can be mixed flow also. Now you see the picture, it is taken from Schlumberger website, and it is having one shaft. You see the big shaft is here. I'm drawing with red line. You can see this one shaft. Okay, and shaft is connected to impellers. Where are the impellers? Impellers will be like this. You see, this is impeller actually. Okay, impellers are like this. Okay, impellers are like this. So impeller, what is the purpose of impeller? Impeller is giving energy to the fluid. Okay, So impeller, then impeller will be connected to diffuser. So it is going to diffuser. Okay, then again impeller, then diffuser, then impeller, then diffuser, impeller, diffuser. So fluid will be moving like this. Impeller is doing like this, diffuser will be bringing back, impeller will be doing like this, diffuser will be bringing back. Okay, so fluid will be moving like this. So away from shaft, again nearby shaft, away from shaft, nearby shaft. Diameter is limited, so fluid will be moving radially. If it is radial flow impeller, if it is mixed flow impeller, that will it will make 45-degree angle. Okay, so this picture, this is showing more mixed flow impeller, I guess, 45-degree. Okay, and what is happening? This is impeller I actually. Impeller I. Okay, impeller I, fluid is entering there, then impeller exit. Okay, from impeller fluid will be exiting, then it will be entering to next diffuser. Okay, so diffuser entry, from diffuser entry, entering, exiting, diffuser entry, then diffuser exit, then again impeller. So diffuser exit will be there. Okay, diffuser exit means this fluid will be nearby shaft. Again impeller entry, going away, again diffuser pushing it like this. And purpose of diffuser is to increase pressure head. Impeller is giving velocity head, impeller is giving velocity head. Impeller, this is impeller giving velocity head. Okay, velocity head or pressure you have converted. Head means amount of liquid column it is developing, and diffuser, it is developing a pressure head, static pressure head. Okay, so impeller giving velocity, impeller, because of kinetic energy, impeller is giving lots of energy to the fluid, but diffuser is not giving. Diffuser is connected to your outer casing. Okay, so diffuser will be connected to your outer casing. Okay, so this is multi-stage, actually this is multi-stage centrifugal pump. Multi-stage centrifugal okay, and you can say ESP or electric submersible pump. Okay, so multiple stages are there. Here I have shown this one also. I think you can remember in the previous lecture. I'll open it. Just please wait. Yeah, so it is connected to a shaft. Actually shaft is like some specific hexagonal shape, so that impeller can rotate with it. Okay, so shaft will be connected to your motor. Motor will be giving rotation. Because of rotation, it will whole things will be rotating. Okay, now let's see one impeller. This is one very thin plastic made impeller. Fluid is entering to impeller I. It is going through the channel, it is going out, so it is exit. Impeller entry, exit. Okay, so if I have radial flow impeller, then fluid will be making like I have shaft, and radial flow impeller means impeller will be making flow path like this. Then diffuser will be there, diffuser entry, impeller entry, diffuser entry, impeller entry. So fluid will be moving like this, like this. Okay, and again it is not two-dimensional. If I have one shaft here, it is not two-dimensional, actually it will be rotating. Okay, impellers are curved, but for representation purpose I am drawing a two-dimensional figure. Okay, one impeller, one diffuser called one stage. So here I have one stage like this, impeller entry, diffuser exit. So this is stage 1. Then here to here entry exit, so stage 2. Okay, so it will have, I have impeller, diffuser is this white part you can see. So fluid exiting from the impeller, then entering from the top of the diffuser, and it going to nearby shaft. Okay, it will be connected like this. Okay, so impeller sucking fluid going vertical, then exiting from here. After exiting, it will be entering. This white portion is having a hole here. So from here, fluid entering, going through this, and it is exiting from here. So this is your impeller and diffuser. One stage, fluid entering, going vertical, entering diffuser, and it is coming axially again. Again, next stage will be there. I'll have another stage. Okay, so one stage going there, going again, going. So fluid is moving like this. Okay, actually it is three-dimensional. So what is happening there? Fluid entering actually vertically, again going vertically. Vertically means perpendicular to the axis. Again entering to next stage impeller, going there, again turning. So this turning is happening. So turning is not like two-dimensional, it will be three-dimensional. It is going like this, it will be turning, again turning, again turning. So that sort of thing happening. So whatever impeller shape is there, diffuser shape also like this, it will have curvature. Okay, so one stage is developing, like say 5 bar pressure. Then I have 1 2 3 4 5 6 7 stage. 7 into 5, 35 bar pressure it will be producing. Okay, okay, let's go to next. Okay, let's go to some formula. You know the basic now. Let's go to formula. Mass conservation, momentum conservation, and energy conservation. Okay, whenever you are going for a fluid mechanic analysis for pumping systems or fluid flow analysis, so these three equations will be universally fixed. You cannot destroy mass, you cannot destroy momentum, you cannot destroy energy. So energy, for example, there will be some losses. Losses does not mean this is you're destroying. Actually, energy is getting converted in certain form which you cannot use. What is the mass conservation? If you are not Einstein, then mass will be fixed actually. Okay, Einstein equals mc square. Their mass is destroyed because this atomic change is happening. But here we are not going for atomic changing or no molecular changing. We are just transferring fluid from one point to another point. So mass will be fixed for our calculations. What is the mass conservation equation? Mass conservation equation is Q equals AV equals A1 V1 equals A2 V2. A means area, V means velocity. Okay, A1 V1, so this is 0.1, this is 0.2, so A2 V2. Okay, the 0.1 flow rate is Q1, then it will be Q2. Okay, and area A1, so velocity will be V1. 0.2, again you are getting Q2, A2, V2, and relationship is the A1 V1 equals A2 V2. You are not destroying mass. Okay, if you are changing density, for example the compressible fluid, so in that case rho term also will be coming. Okay, if density is not varying, say water or oil, not so much pressure difference is there, so we are assuming density almost constant, so in that case there is no variation. So momentum conservation, if some body is moving at certain velocity, it will have certain momentum because it is having mass and velocity, so that product is momentum. So formula is that summation of fx equals rho q vx2 minus vx1 summation of fy, y direction, rho q again vx2 vy2 minus vy1 summation of fz, so z is direction actually, rho q vz1 vz2 minus vz1. So the parameters are fluid flow rate, this is flow rate, this is density. Okay, density, this vx, vy, vz, these are actually component of average velocity in x, y, z direction. Vx, vy, vz components of velocity, average velocity in x, y, z direction. okay, and Fx, Fy, Fz, that says the component of momentum in XYZ direction. J, okay, conservation of energy. Now see the equation for conservation of energy. It will be like J Q12 plus W12 equals J U2 minus U1 plus P2 minus P1 divided by gamma plus V2 square minus V1 square by 2G plus Z1 minus Z2. Okay, so the terms are J is mechanical energy equivalent of heat. Okay, energy equivalent to heat and equivalent of heat. U is internal energy. U is internal energy. Internal energy. And Z is elevation. Z is elevation, and gamma is specific weight of the fluid. Specific weight, WIGHT, of the fluid, and P is a pressure, you know that. Okay, so this actually similar formula you have seen in your Bernoulli's equation. There we said like there is no energy transfer actually. If energy transfer is happening, then actually whole equation will be like this. But let's say there is no heat energy transfer, so in that case actually it will be resembling directly your Bernoulli's equation, like venturimeter calculation you have done. You can remember. Okay. Some more parameter. Viscosity. Already we have discussed tau mu du dy, that formula you know already. So this is related to viscosity. So viscosity we have discussed already in your previous lectures. So there we have seen Newtonian, non-Newtonian fluids. So for details just please go through the previous lectures. Reynolds number also again the formula already given, mu v d by nu, Re equals V d by nu. Okay, a specific speed formula also given, ns, the pump specific speed actually, n root over q bar h 3 by 4. That formula you have seen. So in previous lecture we have discussed. Theoretical head. So theoretical head, when you are calculating, let's say one pump impeller diameter, and let's say impeller diameter is d and speed is n, then what will be theoretical head? So theoretical head normally the formula is like head equals zeta u square by 2g. What is u? U equals omega into r. What is omega? 2n pi by 60. R equals R equals d by 2. Okay, we are assuming that impeller eye diameter is sufficiently small and the impeller outer diameter is larger. So this is the approximation formula, and zeta is the efficiency or coefficient. Okay, efficiency of the pump or impeller. Okay, if you know impeller efficiency, so normally we, for calculation purpose for thumb rule, 65% or 70% we take within that range. Okay, efficiency we should not take very low, or we should not say 80-90%. Normally the ESP system efficiency will be 65 plus minus. Okay, and n should be in RPM, n in RPM. Okay, then you can get head. So if you have RPM, if you are giving in meter, then head will be in meter directly. Okay, and this is theoretical head. What will be the volumetric ratio of practical head and theoretical head. So practical head, actually from you have to get data from your experiments, then you compare your theoretical head and how much difference you are getting, so you can calculate. Hydraulic losses. So there will be several losses in ESP systems. One is that mechanical losses. Mechanical losses. Okay. Another will be like disc friction losses. Okay. Next is your friction calculation. Actually already you have seen in previous lectures, frictional pressure drop. Frictional pressure drop you have seen in our head, you can say, in previous lectures, F L V square by 2 G D. So if length of pipe okay, so why this formula is required? For example, we are calculating suction head requirement, NPSH, how much pressure drop is happening in the suction area, or how much pressure is required to deliver fluid from certain point to certain point. So in that case you need to calculate your pressure drop through the pipe. So this is the pressure drop formula. This is friction factor. Friction factor we have calculated already, so just I am giving formula here. Length of pipe and V is the velocity of fluid, velocity of fluid, and G is gravitational constant, and D is the diameter of pipe. Okay, so you have to check the units, and F value you can get from the table, that friction factor table. You have that chart is there, so you can use the chart, or there are some formula for laminar flow, some turbulent flow, you can use that one. So for detailed analysis of, for detailed formulation, you go to the previous lecture, please. Okay, so this every time I select pump curve and we have designed and we have tested. So here I have taken from Schlumberger website. Actually the company has given in their product brochure, one product name is M series. They have several pumps, different size, and for different condition they made several series of pumps. So one series is M675A pump specification they have given. For that they have given this pump curves. Okay, the characteristic curves. Okay, so here you can see this is head and this is power, this is eta. Okay, head curve is this one. You can remember the head is gradually going down, so if I do not write, still you can understand this is head, and efficiency, it will go maximum, it will go down. Okay, so this curve is showing efficiency curve. Okay, it is going maximum then going down. And what about power? Power will be all increasing actually. Fine. Now best efficiency point, you see the efficiency curve is here, right? This is efficiency curve. So efficiency for eta curve, maximum point is here, you see this. Okay, so this is called best efficiency point, or BEP, or best efficiency point. Fine. Now best efficiency point, you cannot run the pump, so you have to run little bit below and little bit up. Within that range you can run the pump. So what is your operating range? Operating range should be this one, this yellow shaded area, you can see this one. Okay, this is your operating range. And at best efficiency point, what is your head? Then if this is your best efficiency point, your head will be like this. You go to this, so it will be 115 around. Okay, and at the point how much power is there, again you go there, you come down, you have one line here. Okay, so you draw this line and go there. This is a power curve, so it will be 20, 30, 40, it will be like 25 around. Okay, so at best efficiency point you are getting power 25 around. So if you are running pump, let's say of the BP, left side or right side. So in that case your power is changing, but major effect is happening in head. And if you are not running pump at best efficiency point, the result will be you can get more cavitation, more vibration, more failure. Okay, and energy consumption also will be higher. Okay, you can see this. If you are increasing right side of the curve, then energy consumption increasing actually. So your target should be to run the pump at best efficiency point. And specifications, we're discussing many things for ESP systems. You see the specification here. Flow rate is given barrel per day 60 hertz 60 hertz frequency, and here 25,000 barrel. Okay, flow rate 25,000 barrel per day. Okay, and they have written unit BBL per D. Okay, so B per D or BBL per D, so but same actually. And if you are using meter cube per day, there's a different unit is given. Okay, so if people understand meter cube per day, so that's why the company has given both the data. And head per stage head is given feet at 60 hertz. It is writing 112 feet head. Okay, so very good head actually is there. Most probably outer diameter is very high for impeller. Yeah, it is given general outer diameter is 8.62, so larger diameter pump actually, because of larger diameter, and it is rotating at 3600 rpm. RPM not given, I think. Not given. So because 60 hertz, so normally we assume it is 3500 rpm. Okay. So efficiency also very good, 74% around. Okay, so pump efficiency. I said 65 to 70, but it is showing 73. So they have designed a very good pump. Required horsepower 60 hertz. How much horsepower is required? 29, about 30 horsepower required. And head per stage 112. Stage geometry, mixed flow impeller they're using. So presently, whatever I am showing, this one or my ESP system, we have radial flow. This one radial flow. Okay, radial flow means fluid is turning perpendicular 90 degree, but mixed flow means the fluid is not turning 90 degree, is 45 degree. So your impeller length will be longer for mixed flow impeller. Okay, radial flow means directly 90 degree. So this total stage length will be lower for this one. But for mixed flow impeller is going like this and going like this. So total length will be increasing. Okay, but what is the benefit of mixed flow impeller? Mixed flow impeller will be giving higher flow rate. Okay, head will be little bit lower, but flow rate will be higher. Okay, that's why they're using this mixed flow impeller, not radial flow. And metallurgy, stage metallurgy, so they are using this type nickel resist 5530 alloy. So they have some code of alloy, you can go through that. Housing metallurgy, carbon steel, like housing, outside casing, all these things they made using carbon steel. Okay, red alloy, premium alloy. Okay, now shaft diameter, they have shaft diameter 1.37 inch. Okay, normally shaft diameter will have 1 inch or less than 1 inch, but because it is larger diameter pump, so shaft diameter is 1.37 inch, more than 1 inch actually, almost 1.5 inch. Shaft material, Inconel. Okay, so high strength material Inconel they are using. Shaft radial support option. Okay, pump construction, enhanced compression design, factory shimmed. Okay, so this manufacturing method also they have written about the pump. So now if you take any specification chart from any company, you should understand maximum of the things. Okay,